Welcome to the session on differentiation using second derivatives. The objectives for this session are to use the second derivative to describe the behaviour of a function. The second derivative can be used to determine if a curve is concave or convex on a given domain. A function f of x is concave on an interval if and only if f double dash of x is less than or equal to 0 for every value of x in the interval. And a function f of x is convex on an interval if and only if f double dash of x is greater than or equal to 0 for every value of x in the interval. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. In this example, we are required to determine whether y equals x squared plus 3 is concave or convex. So let's solve this. We have y equals x squared plus 3. And this looks something like the diagram you can see on your screen. This implies that dy dx equals 2x. And d2y dx squared is equal to 2. Since d2y dx squared is greater than 0, we know that the function is a convex function for all x in the real numbers. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. In this example, we're required to determine whether y equals minus e to the power 2x is concave or convex. So let's solve this. Here's a sketch of y equals minus e to the power 2x. We can, of course, find dy dx by differentiating y to give us dy dx equals minus 2 times e to the power 2x. Differentiating this again gives us d2y dx squared equals minus 4 times e to the power 2x. This is of course less than 0, and therefore the function is concave for all x in the real numbers. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. In this example, we are required to find the interval on which y equals x cubed minus 8x squared plus 15x is concave and convex. So let's solve this. So here's our expression for y. It will look something like the sketch you can see on your screen now. If we differentiate this, we have that dy dx is equal to 3x squared minus 16x plus 15. And differentiating again gives us d2y dx squared equals 6x minus 16 plus 0. And so if we solve for d2y dx squared equals 0, we obtain x equals 8 over 3. Remember that a function is concave if its second derivative is less than or equal to 0. Therefore, this function is concave for all x less than or equal to 8 over 3. We also know that the function is convex when the second derivative is greater than or equal to 0. In other words, this function is convex when x is greater than or equal to 8 over 3. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's take a look at part A first. We are required to find the interval on which the function y equals sin x is concave on the interval 0 less than x less than 2 pi. So let's solve this. We have that y equals sin x, and therefore dy dx equals cos x, and d2y dx squared equals minus sin x. The graph of y equals minus sin x looks something like the graph you can see on your screen now. Now for the function to be concave, we must have that d2y dx squared is less than or equal to 0. Minus sin x is less than or equal to 0 in the interval 0 less than x less than or equal to pi, and therefore the function is concave in this interval. Now let's take a look at part B. We are required to find the interval on which the function y equals sin x is convex for x greater than 0 and less than 2 pi. So let's solve this. We have y equals sin x, and therefore dy dx equals cos x, and d2y dx squared equals minus sin x. The graph of minus sin x looks something like the graph on your screen you can see now. For the function to be convex, remember that d2y dx squared must be greater than or equal to 0. This implies that minus sin x must be greater than or equal to 0. And this occurs in the interval x greater than or equal to pi less than 2 pi. So here are our definitions of concave and convex again. A point of inflection is the point at which a curve changes from being concave to convex, or vice versa. A point of inflection is a point at which the sign of f double dash of x, or the second derivative, changes. To find a point of inflection, show that f double dash of x equals 0 and show the signs on either side of this point are different. Remember that the point of inflection is not necessarily stationary. Let's now take a look at an example to illustrate these definitions. The diagram on your screen shows a sketch of the function y equals x cubed minus 6x squared minus x plus 30. If we differentiate this, we obtain dy dx equals 3x squared minus 12x minus 1 plus 0. Differentiating again gives us d2y dx squared equals 6x minus 12 plus 0. Now d2y dx squared equals 0 when x equals 2. And d2y dx squared is less than or equal to 0 when x is less than or equal to 2. We can also deduce that d2y dx squared is greater than or equal to 0 when x is greater than or equal to 2. So the function goes from being a concave function to a convex function when x equals 2. This brings us to the end of this session. If you have understood its contents, you should be able to use the second derivative to describe the behaviour of a function. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.